Erwin Schrödinger's revolutionary role in developing wave mechanics begins not with a sudden spark of genius, but with a long, complex struggle to understand a world that defied every rule classical physics had laid down. In the early 20th century, the scientific landscape was full of unresolved mysteries. Atoms did not behave like miniature solar systems, light acted like both waves and particles, and electrons refused to follow predictable, classical paths. Physicists were surrounded by observations that made no sense within Newtonian intuition. For Schrödinger, a man deeply influenced by mathematics, philosophy, and the desire for visual clarity, this era of confusion became the soil in which a radical new theory would grow. He sensed that nature's smallest components were whispering a new language, and while others tried to decode it with abstract symbols or discrete jumps, Schrödinger chose to imagine a universe shaped by continuous, fluid waves. His journey began with dissatisfaction. The quantum theory proposed by Niels Bohr and extended by others relied heavily on abrupt, unnatural quantum jumps, where electrons seemingly teleported between fixed orbits. To Schrödinger, this felt more like a temporary patch than a fundamental truth. He longed for a model that offered elegance, continuity, and deeper meaning. Then came Louis de Broglie's bold suggestion that electrons were not simply particles but also waves, possessing a wavelength related to their momentum. This idea captivated Schrödinger. Something in it resonated with his desire for unity and coherence. If electrons had wave-like properties, then perhaps the universe itself could be described not through rigid mechanical pathways, but through mathematical waves spread across space. Schrödinger did not simply accept de Broglie's insight, he built an entire new structure around it. Retreating to the Swiss Alps for solitude and clarity, he carried with him only de Broglie's doctoral thesis and his own relentless curiosity. The quiet mountains became his laboratory, and the equations he scribbled in notebooks there would soon overturn the foundations of physics. He imagined electrons not as tiny corpuscles orbiting a nucleus, but as vibrating patterns, standing waves that existed throughout the atom. His next step was monumental: to formulate a mathematical equation that described how these waves change over time. The result was the Schrödinger equation, a masterpiece of scientific thought that linked energy, momentum, and wave behavior into a single expression. This equation did something extraordinary. It allowed scientists to calculate the exact behavior of atomic systems not in terms of precise trajectories, but in terms of probabilities and wave functions. For the first time, the mysteries of quantum behavior had a consistent, predictive framework. The electron in the hydrogen atom was no longer a point-like particle confined to an orbit. Instead, it was a cloud-like wave of probability spread out in space, each region representing the likelihood of finding the electron there. Schrödinger's waves were not physical waves like ripples on water, they were mathematical waves, describing the underlying state of a system. Yet they offered a clarity and visualizable structure that many physicists had been craving. When Schrödinger published his results, the scientific world reacted with a mixture of excitement and disbelief. His wave mechanics provided solutions to long-standing problems that had stumped even the greatest physicists. It successfully reproduced the energy levels of hydrogen, something Bohr's model had managed only with conceptual gymnastics. But Schrödinger's approach was different. It arose naturally from the mathematics. It felt fundamental. It felt true. Many scientists welcomed this new perspective with open arms. Max Born, Wolfgang Pauli, and other giants of the field immediately recognized the power of the method. Wave mechanics began to spread across the scientific world like a shockwave, rewriting textbooks and redefining research. But Schrödinger's contributions extended far deeper than a single equation. His work reintroduced the idea of continuity into quantum theory. For decades, classical physics had been built on the notion that nature moves smoothly, without sudden breaks. Quantum theory, in contrast, had embraced discontinuity. Particles jumped, energies were quantized, and measurements seemed to disrupt reality itself. Schrödinger sought to restore a sense of unity by showing that quantization could emerge naturally from the wave nature of matter. Electrons did not jump between orbits. Instead, the allowed energy states came from the boundary conditions imposed on standing waves within the atom. Just as a violin string vibrates only in certain harmonics, an electron wave could occupy only certain stable patterns. These patterns, now known as wave functions, became the central objects of quantum mechanics. Schrödinger's wave mechanics offered something no other early quantum theory had achieved: a visual, intuitive picture of the microscopic world. Instead of isolated particles moving unpredictably, one could imagine gentle waves spreading, combining, interfering, and forming patterns of astonishing beauty and complexity. These ideas would eventually evolve into three-dimensional orbitals, the shapes that represent electron distributions around atoms, shapes that define chemistry, bonding, and the behavior of matter itself. All of these concepts trace their origins back to the moment Schrödinger realized that electrons could be waves. Yet Schrödinger's work was not accepted without challenge. The most notable opposition came from Werner Heisenberg, whose matrix mechanics represented a completely different approach to quantum theory. Heisenberg's formalism was abstract, mathematically sophisticated, and stripped of any visual interpretation. Schrödinger's wave mechanics, by contrast, appealed to physicists who preferred intuitive, spatial representations. For a time, two competing visions of quantum reality stood side by side. But as more research unfolded, it became clear that both approaches were mathematically equivalent. This realization helped unify the quantum community and solidify the foundations of modern physics. Despite this unification, Schrödinger remained uneasy about certain implications of his own theory. The interpretation promoted by the Copenhagen school, especially Bohr and Heisenberg, suggested that the wave function represented only probabilities, not physical reality. Schrödinger resisted this idea, insisting that the waves had real meaning. His discomfort with probabilistic interpretation would eventually lead him to create his famous cat thought experiment, designed to highlight the absurdity of taking probability as the essence of reality. But even though he disputed some philosophical conclusions, nothing diminished the power of the wave mechanics he had introduced. The revolutionary nature of Schrödinger's theory extended far beyond the atomic scale. It opened the door to understanding chemical reactions, molecular structures, and the stability of matter. Without wave mechanics, modern chemistry simply would not exist. The bonding between atoms depends on the overlap and interaction of electron wave functions, forming structures that determine the properties of all materials. Everything from the color of a gemstone to the conductivity of metals depends on Schrödinger's equation. In a very real sense, the world as we know it, its textures, its colors, its chemistry, was explained not by Newton but by Schrödinger. Moreover, wave mechanics became the backbone of countless technologies: semiconductors, lasers, magnetic resonance imaging, and quantum computing all rely on principles that trace back to the idea that particles are waves and that their behavior follows Schrödinger's equation. The digital revolution, every smartphone, every computer chip, owes a silent debt to the mathematical vision Schrödinger brought into reality. His equation is woven into the infrastructure of the modern world, guiding the design of circuits, sensors, and materials. What began as a search for clarity in atomic behavior became one of the most impactful discoveries in human history. At the heart of Schrödinger's revolution lies a profound philosophical shift. He taught the world that reality is not composed of tiny, solid objects moving through empty space. Instead, it is a tapestry of overlapping possibilities, an ocean of wave patterns that interact, interfere, and collapse into definite outcomes only when observed. This idea reshaped not only physics, but the human understanding of existence. Schrödinger's waves, invisible yet fundamental, forced us to question what it means for something to exist, what it means for something to be real, and how observation and consciousness shape the universe we experience. Schrödinger himself remained a unique figure, a physicist, philosopher, and seeker of unity in all things. His development of wave mechanics was not a dry mathematical exercise, but a quest to uncover the hidden harmony of nature. He believed that beneath the apparent randomness of quantum events, there might lie a deeper order, one that we have yet to fully grasp. Whether that deeper order exists remains an open question, but Schrödinger's contribution created the foundation upon which all future inquiries would stand. His revolution was not merely a scientific victory, but a new way of seeing the universe. Where others saw chaos and unpredictability, Schrödinger saw elegant waves shaping the structure of atoms and the fabric of reality. His wave mechanics became a bridge between mathematical abstraction and physical intuition, a bridge that countless scientists would walk as they explored the quantum realm. Even today, every student learning quantum mechanics begins with the Schrödinger equation, just as every researcher in quantum physics relies on its insights. His work endures not simply because it is correct, but because it captures the profound, hidden beauty of the universe. Schrödinger's revolutionary wave mechanics did not just introduce a new mathematical tool, it reshaped the imagination of physics itself. As the scientific community absorbed his work, researchers began exploring an entirely unfamiliar landscape where waves governed particles and where intuition developed from the classical world no longer applied. In those early years, Schrödinger's equation was like a lantern carried through a dark forest, illuminating patterns of behavior that had always existed but had remained invisible. Physicists discovered that the atom was not simply a miniature planetary system, but a vibrational pattern, a place where waves formed nodes, harmonics, and standing structures. This new understanding resolved puzzles that had haunted atomic theory for decades. Why did atoms emit light only at certain frequencies? Why were some arrangements of electrons stable while others were not? Wave mechanics showed that these features arose naturally from the permitted wave patterns around the nucleus, not from arbitrary rules or ad hoc hypotheses. As the implications spread, Schrödinger's work began influencing other fields of science. Chemists, who once struggled to explain the structure of molecules using classical ideas, found that wave mechanics provided a beautifully consistent explanation for chemical bonds. The mysterious forces that held atoms together within a molecule were now understood as the sharing and interference of wave functions. When electron waves overlapped constructively, atoms bonded. When they interfered destructively, bonds weakened or broke. Shapes of molecules, reaction pathways, and the stability of matter could be predicted with unprecedented accuracy. What had been an almost mystical branch of science became grounded in the mathematics of waves, allowing chemistry to advance rapidly into a more precise and predictive discipline. In physics itself, Schrödinger's impact deepened as researchers applied his equation to more complex systems, multi-electron atoms, molecules, solids, and even nuclear particles. Wave mechanics grew into quantum mechanics, a complete and unified framework that offered unmatched predictive power. Every time physicists uncovered a new phenomenon in the microscopic world, Schrödinger's equation was there to guide understanding. It became an intellectual compass pointing toward the behavior of nature at its most fundamental level. This universality of application demonstrated the robustness of Schrödinger's insight and cemented it as one of the greatest scientific achievements of all time. But what truly set Schrödinger apart was not only the creation of wave mechanics, but the philosophical depth with which he approached his own discoveries. He refused to accept a shallow interpretation of the wave function as merely mathematical. He believed the waves represented something real, something connected to the fabric of existence itself. His dissatisfaction with the probabilistic interpretation of quantum mechanics revealed the complexity of his mind. While he accepted that his equation predicted probabilities, he resisted the idea that probability was all there was. To Schrödinger, the universe could not be built on uncertainty alone. There must be an underlying reality beneath the wave function, a deeper truth that the mathematics only hinted at. This conviction led him into long-standing debates with the Copenhagen school, who insisted that quantum mechanics had no hidden reality beyond measurement outcomes. These debates were not minor disagreements, but reflections of a profound philosophical divide. Schrödinger believed in continuity. Bohr and Heisenberg believed in fundamental discontinuity. Schrödinger favored visualizable models, the others embraced abstraction. Schrödinger sought physical meaning, they sought operational accuracy. In the end, both sides contributed to the theory's development, but the tension between them enriched the intellectual landscape and pushed quantum mechanics to mature. Schrödinger's insistence on clarity influenced generations of physicists who continued searching for deeper interpretations, leading to theories like Bohmian mechanics, many worlds interpretation, and quantum information approaches. Without Schrödinger's challenge, the philosophical exploration of quantum foundations might never have flourished as it has. Wave mechanics also had profound implications for the concept of measurement. Schrödinger realized that the act of observing a quantum system changed it, collapsing the wave function into a definite state. This idea unsettled him, as it seemed to assign a mysterious role to the observer, potentially even linking consciousness with physical processes. He resisted these implications, but they became central to quantum philosophy. His own wave mechanics had opened a door that led to questions no physicist had ever asked before. What is reality when no one is looking? Does the universe exist in a spread of possibilities until it interacts with something? What determines which possibility becomes real? These questions remain among the greatest unsolved mysteries of modern science, and they exist because Schrödinger's equation forced the world to confront them. Despite his philosophical discomfort, Schrödinger's contributions to the practical side of physics were massive. His equation became the foundation for the study of quantum fields, condensed matter, superconductors, superfluids, and countless other phenomena. When scientists discovered that materials could conduct electricity with zero resistance at low temperatures, it was wave mechanics that explained the formation of Cooper pairs and quantum condensates. When physicists explored the behavior of electrons in crystals, it was Schrödinger's equation that led to the understanding of energy bands and electronic properties. These insights built the technological world around us. Computers, lasers, sensors, medical imaging, and communication networks all rely, directly or indirectly, on Schrödinger's framework. Even the microchips powering modern devices function because engineers learned to manipulate electrons according to quantum wave rules. Few scientific theories have ever had such profound and widespread influence. As quantum mechanics expanded, Schrödinger's wave-based vision continued to blend mathematics with artistry. The wave functions he introduced took on shapes of great beauty, delicate patterns of probability that became the language of atomic orbitals. These patterns were not arbitrary, they reflected the deep harmony of the quantum world. For many scientists, these visualizations provided a way to connect with the abstract realm of electrons and atoms. Schrödinger brought imagination into physics, showing that even the smallest components of the universe could exhibit stunning complexity and elegance. His waves transformed the invisible world into something that could be pictured, imagined, and taught, making quantum mechanics accessible to generations of students. Schrödinger's personal intellectual style also shaped the future of science. He was not content to isolate physics from the broader questions of existence. He drew inspiration from biology, philosophy, and Eastern thought, often seeking a unified understanding of life and matter. This interdisciplinary vision would later influence many thinkers who recognized that quantum mechanics might not only describe particles, but also illuminate deeper questions about consciousness, information, and the nature of mind. While Schrödinger never claimed that quantum mechanics directly explained life, he suggested that wave-like processes might be essential in biological systems. His later work in What is Life? inspired molecular biologists and eventually influenced the discovery of DNA's structure by Watson and Crick, who acknowledged Schrödinger's ideas as a source of inspiration. In this way, the impact of wave mechanics extended far beyond physics, shaping entire fields of scientific discovery. The revolutionary transformation that Schrödinger initiated did not end with the establishment of quantum mechanics. It continues in modern research, where scientists apply his equation to increasingly complex systems. Quantum computing, one of the most promising technologies of the 21st century, depends fundamentally on the superposition principle his wave mechanics introduced. Quantum bits, qubits, behave as Schrödinger waves existing in multiple states simultaneously. Entire companies, research labs, and industries now build on principles that trace directly back to Schrödinger's original insights from the Alps. In quantum communication, teleportation, cryptography, and sensing technologies, Schrödinger's influence is unmistakable. The idea that reality can be described as a wave of possibilities is no longer a philosophical curiosity. It is the foundation of emerging technologies that may reshape society in ways as significant as the classical revolution of the 17th century. The magnitude of Schrödinger's achievement becomes even clearer when we consider the state of physics before his contributions. Theoretical frameworks were disjointed, phenomena were poorly understood, and progress was often driven by intuition rather than coherent structure. Wave mechanics provided a unifying language that integrated scattered observations into a complete worldview. It taught physicists not just how to calculate results, but how to conceptualize the quantum world. Without Schrödinger, the field might have remained fragmented for decades. Instead, his equation brought order and mathematical harmony, allowing scientists to build layer upon layer of new knowledge. As the decades passed, Schrödinger's wave mechanics became so fundamental that many forgot it had been controversial. It became embedded in textbooks, research, and education as the standard approach to quantum systems. Yet the originality and audacity of Schrödinger's breakthrough remain astonishing. He defied prevailing views, challenged established theories, and insisted on mathematical elegance in a field dominated by contradictions. His courage to imagine a wave-based universe reshaped physics at its core. Even today, every new experiment conducted in the quantum domain pays silent tribute to the mind that first captured the behavior of particles in the language of waves. Schrödinger's story is not just one of scientific innovation, but of human curiosity and intellectual bravery. He looked at the chaos of early quantum theory and dared to envision harmony. He saw mystery where others saw contradiction, and he transformed that mystery into understanding. His wave mechanics became one of the greatest pillars of modern science, a foundation upon which entire disciplines rest. Through his insight, the hidden world of atoms became comprehensible, predictable, and profoundly beautiful. His legacy is not only in the equation that bears his name, but in the vast universe of ideas, technologies, and discoveries that grew from it. Schrödinger changed the way humanity understands nature, revealing that beneath the surface of matter lies a world governed not by certainty, but by elegant, flowing waves of possibility. From the moment Erwin Schrödinger stepped into the developing world of quantum physics, he was surrounded by theories that strained the limits of classical thought. For centuries, science had assumed that nature behaved in predictable, deterministic ways. Every motion had a cause, every particle had a definite position, and the universe unfolded like a grand mechanical clock. But the early quantum discoveries, strange spectral lines, unpredictable electron behavior, and the dual nature of light, made it clear that this comforting picture of reality was beginning to crumble. Schrödinger entered this world not as a passive observer, but as a challenger of tradition. He sensed that the classical framework was too rigid to contain the mysteries being uncovered, and he began to shape a new perspective where probability replaced certainty, and the familiar laws of motion dissolved into something far more subtle. At the heart of his challenge to classical ideas was the recognition that the microscopic world could not be explained with the precision and determinism that governed everyday experience. Classical physics assumed that if one knew the initial position and velocity of a particle, one could predict its future with absolute accuracy. But experiments revealed that electrons behaved in ways that defied this logic. When passed through a narrow slit, they formed interference patterns like waves. When measured, they appeared as particles. They seemed to exist in a state of ambiguity, neither here nor there, neither wave nor particle, until forced into a definite condition through observation. Schrödinger realized that classical principles were simply inadequate. Something fundamentally new was needed. Something that embraced uncertainty rather than resisted it. The concept of quantum probability did not emerge from a single experiment, but from a series of puzzling phenomena that accumulated like clues to a mystery. Scientists observed electrons vanishing from one energy level and appearing at another without passing through intermediate steps. They saw photons behaving like waves in one moment and particles in the next. These contradictions demanded a deeper interpretation. Schrödinger felt that rather than treating probability as a temporary mathematical trick, physicists needed to recognize it as a central feature of nature. This was a radical departure from classical thinking. Probability had always been seen as a sign of ignorance, a placeholder until more information could be obtained. Schrödinger's work suggested something revolutionary, that probability might not be caused by human ignorance, but might instead be woven into the fabric of reality itself. His wave mechanics brought this idea to life with mathematical elegance. The wave function he introduced was not a simple description of a particle's motion. It was a probability landscape, a depiction of where a particle was likely to be found. Instead of a precise trajectory, Schrödinger offered a distribution of possibilities. Classical physics demanded a single outcome. Quantum physics offered a spectrum of potential outcomes, each with its own likelihood. This shift was not merely a change in mathematical language, it was a transformation in worldview. The universe, once thought to be rigid and predictable, now appeared fluid, uncertain, and governed by laws that dealt in probabilities rather than certainties. Schrödinger's challenge to classical ideas became even clearer when he analyzed how particles behaved in quantum systems. In the classical world, an object either occupies a location or it does not. In quantum systems, the wave function allows particles to exist in multiple states simultaneously. An electron in an atom does not occupy one precise orbit. Instead, it exists in a superposition of possible positions, spread out like a cloud. Schrödinger's mathematics visualized this cloud in ways that classical physics could never achieve. Each region of the cloud represented a probability, a measure of where the electron might be if one attempted to observe it. Before observation, the electron was not at any single point. It existed as a blend of possibilities. The classical notion of reality, fixed, solid, deterministic, was replaced by a dynamic, evolving wave of probabilities. Yet Schrödinger's embrace of probability was not easy or complete. He himself struggled with the philosophical implications of the quantum world. His equation suggested that particles existed as waves of possibility, but he found it troubling that these waves collapsed into definite outcomes during measurement. He questioned what caused the collapse, what triggered the transition from probability to certainty. Classical physics had no such problem because it insisted that particles always had definite values. The quantum world, however, demanded an explanation for how and why probabilities turned into facts. Schrödinger's discomfort with this mystery later inspired him to design thought experiments that exposed the limitations of classical reasoning. He believed that by highlighting the strange consequences of quantum probability, he could force physicists to confront the deeper question of what reality truly was. One of the most striking features of Schrödinger's challenge to classical ideas was his insistence that the wave function represented something real and meaningful. Many of his contemporaries saw probability as a convenient shorthand, a way of calculating results without looking for deeper meaning. But Schrödinger argued that the wave function was not a mere mathematical tool. It was the core of physical reality. It described not the limits of human knowledge, but the actual state of a system. This belief set him apart from the Copenhagen interpretation, which argued that probability was merely a reflection of what could be known, not a property of nature itself. Schrödinger saw this view as incomplete and unsatisfying. For him, the wave function was not a shadow of reality, it was reality. The difference between classical and quantum probability became even more dramatic when Schrödinger's ideas were applied to experiments involving interference. In classical physics, if particles pass through two slits, each particle must pass through one slit or the other. But quantum experiments showed that electrons behaved as if they passed through both slits simultaneously. They created patterns of interference on a screen, patterns that could only be explained if the particles existed in multiple states at once. Classical reasoning could not account for this. Schrödinger's wave function, however, described it perfectly. The probability amplitudes associated with each pathway combined, interfered, and produced a pattern. This was not randomness in the classical sense. It was structured probability that followed precise mathematical rules. This new form of probability was unlike anything seen in the classical world. It was neither chaotic nor unpredictable. Instead, it behaved with stunning regularity, obeying equations that described how waves added, canceled, and reinforced one another. Schrödinger's challenge to classical ideas was not merely the introduction of uncertainty. It was the revelation that uncertainty itself could be ordered, mathematical, and predictive. He showed that probability was not the enemy of science, but one of its most powerful tools. Another profound aspect of Schrödinger's challenge was the implication that no particle possessed definite properties until measured. Classical physics assumed that a particle always had a position, a momentum, and other attributes. Quantum theory, in the Schrödinger framework, suggested something far stranger, that particles did not possess such properties until interaction forced them into existence. Before measurement, there was only the wave function, a fluid entity representing immeasurable potential. In this sense, Schrödinger's work implied that reality itself might be incomplete without interaction. Observation did not reveal a pre-existing fact, it helped create that fact. This idea shattered classical assumptions about an objective universe existing independently of observers. Schrödinger's introduction of probability also influenced how scientists understood time and change. In classical physics, time was a steady progression of cause and effect. In quantum physics, the evolution of the wave function allowed systems to drift among countless possibilities. Time no longer revealed a single predetermined path. Instead, it guided a complex unfolding of potential outcomes, each shaped by probability. Schrödinger showed that the future of a quantum system could be predicted only in terms of likelihoods, not certainties. This was a dramatic shift from the classical expectation that perfect knowledge of the present guaranteed perfect prediction of the future. Yet Schrödinger's challenge did not simply destroy classical ideas, it replaced them with a richer, more flexible understanding of nature. He demonstrated that probability did not weaken physics but strengthened it. His wave mechanics allowed scientists to calculate the behavior of atoms with unprecedented accuracy. It revealed stable atomic structures, chemical interactions, and quantum fields with astonishing detail. Far from being vague or unscientific, quantum probability proved to be one of the most reliable frameworks in the history of science. Through these contributions, Schrödinger redefined the boundaries of what could be known. He taught the world that uncertainty was not a flaw in the universe, but an intrinsic feature. He showed that the classical notion of strict determinism was inadequate, and that the true language of the microscopic world was probability, structured, elegant, and deeply woven into the essence of reality. His work forced humanity to rethink the nature of existence, challenging old assumptions and opening the door to a world governed not by certainty, but by possibility. Schrödinger's exploration of quantum probability carried implications far beyond mathematics. By insisting that the wave function represented reality, he challenged the classical worldview in a way that went to the core of how humans perceive nature. In classical physics, measurement was passive. Observers could, in principle, record a system without altering its state. Schrödinger's wave mechanics overturned this assumption entirely. Observation became an active component of reality, collapsing a superposition of probabilities into a singular, definite outcome. This idea forced scientists and philosophers alike to reconsider what it meant to know something and whether reality exists independently of observation. In embracing probability, Schrödinger suggested a universe that was participatory in nature, one in which potentialities existed as real features, not mere abstractions or placeholders for ignorance. The conceptual shift demanded by quantum probability extended to our understanding of causality. Classical determinism posited a universe in which every event followed inevitably from prior conditions. In Schrödinger's framework, causality was more subtle and probabilistic. The wave function evolved predictably according to his equation, but individual events, whether an electron appears in one region or another, remained intrinsically uncertain. The future was no longer a single thread, but a tapestry of possibilities, each governed by the underlying mathematics of the wave. Schrödinger's insight did not eliminate order, rather, it revealed a new kind of order, one embedded in patterns of probability rather than fixed trajectories. This was a radical reframing of cause and effect, one that influenced not only physics but also philosophy, prompting reflections on the nature of chance, necessity, and the limits of human understanding. The probabilistic approach also changed the way physicists approached prediction. Instead of attempting to pinpoint exact outcomes, scientists learned to calculate likelihoods. Schrödinger's wave function provided a comprehensive map of possibilities, where the squared magnitude at any point indicated the probability of finding a particle there. This quantitative view allowed physicists to make remarkably accurate predictions despite the apparent uncertainty. Spectral lines of atoms, the stability of chemical bonds, and the dynamics of subatomic particles all became predictable in probabilistic terms. Classical mechanics could never have accounted for these phenomena with such precision. Schrödinger demonstrated that uncertainty did not preclude scientific knowledge. It was a new, more subtle form of insight. Schrödinger's challenge also illuminated the paradoxical nature of superposition. Particles could exist in multiple states at once, a concept alien to classical intuition. This was more than a mathematical curiosity, it had profound implications for reality itself. In Schrödinger's view, probability was not a temporary veil over reality, but a fundamental aspect of it. The universe did not simply appear uncertain because humans lacked knowledge. It was inherently indeterminate in the classical sense. The classical world of definite positions and velocities was an emergent phenomenon arising from the statistical behavior of underlying quantum probabilities. Schrödinger's work forced scientists to acknowledge that certainty was an approximation, not an absolute. The thought experiments Schrödinger devised further exposed the tension between classical assumptions and quantum probability. While most famous among these is the cat paradox, it originated from his dissatisfaction with the Copenhagen interpretation, which treated the wave function as merely a tool for prediction rather than a description of reality. Schrödinger wanted to show that taking probability seriously had consequences so bizarre that classical reasoning failed utterly. A system could exist in multiple states simultaneously, leading to outcomes that seemed impossible under deterministic laws. Yet these outcomes followed precisely from the mathematics of probability. The universe, Schrödinger argued, was stranger than anyone had imagined, and understanding it required a willingness to accept that probability, not certainty, governed the most fundamental processes. The mathematical formalism Schrödinger developed reinforced the primacy of probability in quantum mechanics. Unlike Bohr's and Heisenberg's models, which relied on abstract or discrete representations, Schrödinger's wave function was continuous, spreading smoothly across space. This continuity allowed the probabilistic nature of reality to be represented in a tangible form. Interference patterns, diffraction, tunneling, and other quantum phenomena could be directly calculated. Classical ideas, which demanded particles occupy single points in space, could not accommodate such behaviors. Schrödinger's wave mechanics gave a natural explanation, showing that what seemed random in one context was a consequence of underlying probabilities interacting according to precise rules. By doing so, he provided not just a framework for calculation, but a lens through which the very logic of the universe could be understood. Probability also reshaped the perception of energy levels and atomic transitions. In classical theory, an electron orbiting a nucleus should be able to occupy any energy level continuously. Experiments, however, revealed discrete energy states. Schrödinger's wave mechanics explained this as a natural outcome of the wave properties of electrons. Standing waves in the atom allowed only certain configurations, each associated with a specific energy level. The probabilities derived from the wave function indicated where electrons were most likely to be found, and why transitions occurred between specific states. Classical mechanics had no explanation for these constraints, but Schrödinger's probabilistic waves offered both clarity and predictive power. Probability was no longer an inconvenience. It was the key to unlocking atomic behavior. The broader implications of Schrödinger's challenge extended to technology and modern applications. Quantum probability underpins the functioning of semiconductors, lasers, superconductors, and even MRI machines. Engineers rely on the probabilistic behavior of electrons to design circuits, manipulate currents, and control energy flow. Schrödinger's insights provide the foundation for technologies that have transformed daily life, from smartphones to medical imaging. Without embracing probability as an essential feature of nature, these advances would have been impossible. His challenge to classical determinism did not remain theoretical. It became the practical engine driving the quantum revolution. At the philosophical level, Schrödinger's insistence on probability forced a re-evaluation of knowledge itself. Determinism, once the hallmark of scientific certainty, gave way to a universe in which outcomes are contingent, context-dependent, and probabilistically determined. Observation, measurement, and interaction became central to defining reality. Schrödinger's challenge suggested that even at the smallest scales, the universe resists the rigid structures imposed by classical logic. Reality could not be fully captured by any single snapshot or trajectory. It had to be understood as a dynamic interplay of possibilities. This shift was not merely academic. It transformed the way scientists, philosophers, and thinkers approached questions about causation, knowledge, and the structure of the natural world. Schrödinger's approach also highlighted the limits of human intuition. Classical reasoning, grounded in everyday experience, could not predict quantum behavior. Probability, as introduced through wave mechanics, demanded a new form of understanding, mathematical, abstract, and counterintuitive. This represented a profound intellectual challenge, to think in terms of possibilities rather than certainties, to accept that the very notion of a single outcome might be an illusion at fundamental levels. Schrödinger's work trained a generation of scientists to see beyond appearances, to recognize patterns of probability where classical reasoning saw chaos. It reshaped the cognitive landscape of physics, opening minds to a universe governed by chance as much as law. Even as Schrödinger developed the mathematical framework, he remained aware of its philosophical tensions. Probability suggested a universe less deterministic than classical physics had assumed, yet Schrödinger sought coherence and meaning within this uncertainty. He did not abandon reason or logic. He sought to integrate probability into a larger understanding of reality. This nuanced view distinguishes Schrödinger from many of his contemporaries. While some embraced randomness as a convenient tool, he treated it as a profound principle with implications for the nature of existence itself. Probability was not a placeholder for ignorance, but a guide to the deeper structure of the universe. Schrödinger's challenge also forced scientists to reconsider the meaning of state and existence. Classical physics assumed that an object's properties were intrinsic and independent of observation. In quantum mechanics, Schrödinger showed that properties are defined in terms of probabilities, dependent on the entire system and its interactions. This interdependence was foreign to classical thought. Probability became a relational concept, describing how elements of a system influence one another. Schrödinger's wave mechanics revealed that uncertainty is not a deficiency, but a defining feature of nature, demanding new modes of reasoning and interpretation. Through all these contributions, Schrödinger transformed not only physics but the very methodology of scientific inquiry. Experiments no longer simply confirmed deterministic predictions, they explored landscapes of probability. The wave function became both a tool and a guide, pointing to regions of high likelihood and revealing the intricate structure of quantum systems. Classical ideas of rigid causation, absolute trajectories, and definite states were replaced by a more flexible, probabilistic logic. Schrödinger demonstrated that embracing probability could yield clarity where classical assumptions led only to confusion. The microscopic world, once opaque and chaotic, could now be mapped, predicted, and understood, if one accepted that nature operates in terms of possibilities rather than certainties. Schrödinger's challenge to classical ideas did not stop at theory. It reshaped scientific education, influencing how quantum mechanics was taught, understood, and applied. Students learned to calculate probabilities, interpret wave functions, and visualize superpositions, all while abandoning the expectation of classical determinism. The probabilistic perspective became foundational, allowing new generations of physicists to tackle problems that classical intuition could never have solved. In this sense, Schrödinger's challenge continues to resonate, guiding research, technology, and understanding even a century later. His insistence on the centrality of probability reshaped not only equations, but the mindset of science itself, creating a paradigm in which uncertainty is not a weakness, but the very essence of the quantum world. The birth of the Schrödinger equation marked one of the most profound turning points in the history of physics, a moment when the abstract mysteries of the atomic world were given a precise, mathematical voice. Before Schrödinger's contribution, quantum theory was a collection of ideas, experiments, and postulates that, while remarkable, lacked a unified framework. Niels Bohr's model of the atom offered quantized energy levels, and Werner Heisenberg's matrix mechanics provided a formalism to predict outcomes, but both approaches left much to be desired in terms of visualization, continuity, and a sense of underlying reality. Schrödinger, motivated by a desire to reconcile these fragmented insights with a coherent, physically meaningful picture, began to explore the notion that electrons and particles could behave like waves. This insight, inspired by Louis de Broglie's hypothesis of matter waves, would eventually crystallize into a single, elegant equation capable of describing the quantum world in all its complexity. The journey toward the equation was as much philosophical as it was mathematical. Schrödinger sought a framework that could describe particles not as point-like objects traveling in fixed paths, but as distributed entities governed by continuous, deterministic laws. He imagined the atom as a vibrating structure, a place where standing waves could form, interfere, and exist in discrete patterns. These waves were not tangible in the sense of water or sound, but mathematical constructs that encoded the probabilities of particle behavior. His goal was to create an equation that could predict the evolution of these waves over time, giving scientists a tool to calculate the behavior of quantum systems rather than relying on approximations or abstract postulates. The equation he developed, now universally known as the Schrödinger equation, was revolutionary in both concept and application. Its structure was deceptively simple. It related the total energy of a system to its wave function, a mathematical expression representing the quantum state of a particle or system of particles. Yet this simplicity belied the profound implications it carried. Where classical physics described objects with definite positions and velocities, the Schrödinger equation described a probability amplitude spread over space and time, governing the likelihood of finding a particle in any given configuration. In doing so, it provided the first truly comprehensive, predictive framework for understanding atomic and subatomic phenomena. One of the most striking aspects of the Schrödinger equation was its ability to reproduce known results while offering deeper insight. The energy levels of hydrogen, which Bohr had derived using semi-classical reasoning, emerged naturally from the wave formalism without the need for arbitrary assumptions. The equation revealed that the allowed states of an electron were not merely imposed by quantum rules, but arose as natural consequences of the wave patterns constrained within the atomic structure. Standing waves formed around the nucleus, each corresponding to a discrete energy level. This insight transformed the understanding of atomic stability, chemical bonding, and the very architecture of matter. What had once been a set of puzzling observations became a logical and mathematically precise framework. Beyond reproducing known results, the Schrödinger equation opened entirely new vistas of prediction. It allowed physicists to calculate the probability distributions of electrons in complex atoms and molecules, providing a visual and quantitative understanding of chemical structure. Molecular orbitals, electron density clouds, and bonding interactions could now be described and predicted with remarkable accuracy. For the first time, chemists could move beyond simple empirical rules and reason from first principles, grounded in the mathematics of wave behavior. The equation became a bridge between physics and chemistry, uniting two fields that had previously been separated by methodological and conceptual divides. The birth of the Schrödinger equation also represented a shift in how scientists understood determinism and the role of probability in the quantum world. Whereas classical mechanics promised precise outcomes given initial conditions, the Schrödinger equation predicted a spectrum of possibilities, each weighted by its probability amplitude. The wave function, governed by the equation, encoded the complete state of a system, evolving deterministically over time. Yet the results of measurement were inherently probabilistic. This duality, deterministic evolution of probabilities, combined with probabilistic measurement outcomes, challenged classical intuition and forced physicists to think differently about causation, prediction, and reality itself. From a technical standpoint, Schrödinger's achievement lay in the careful translation of physical principles into mathematical form. He recognized that the energy of a particle in a potential could be represented by differential operators acting on a wave function. Kinetic energy, potential energy, and temporal evolution were encoded within the equation, producing a compact representation that captured the full behavior of the system. The mathematics of the equation allowed for generalization to systems of multiple particles, complex potentials, and varying boundary conditions. It became a universal tool applicable to atoms, molecules, nuclei, and even larger quantum systems, providing a unifying language for the entire field of quantum mechanics. The purpose of the Schrödinger equation was not merely to calculate numbers, but to provide a coherent conceptual framework. Schrödinger sought to replace abstract postulates and heuristic models with a theory grounded in continuity, mathematics, and physical meaning. His wave mechanics offered a way to visualize the quantum world, to imagine electrons as waves that occupy regions of space with varying intensity, and to understand the probabilistic outcomes of measurement in a rigorous way. This approach brought a sense of elegance and simplicity to a field previously dominated by contradictions and anomalies. Where quantum mechanics had once appeared fragmented and paradoxical, the Schrödinger equation provided unity and coherence. The development of the equation also had profound philosophical implications. It suggested that the universe at its most fundamental level was not composed of particles with definite properties, but of waves of probability. The reality of matter became an emergent phenomenon arising from the underlying wave function. Schrödinger himself wrestled with these implications, concerned about the philosophical and conceptual consequences of a universe governed by waves rather than particles. His later thought experiments, including the famous cat paradox, were designed to explore and critique the interpretation of the wave function and to highlight the tension between deterministic wave evolution and probabilistic measurement outcomes. The equation, while a technical masterpiece, opened doors to questions about reality, observation, and consciousness that continue to be debated today. Practically, the Schrödinger equation transformed scientific research. It became the foundation for understanding chemical reactions, predicting the shapes of molecules, and explaining the interaction of light and matter. Techniques such as spectroscopy, quantum chemistry, and computational modeling all rely on the principles encoded in the equation. From semiconductor design to materials science, the ability to predict electron behavior with wave mechanics underpins countless technological advances. The equation's purpose, therefore, extends beyond abstract theory. It is a practical tool for understanding, predicting, and manipulating the microscopic world in ways that impact daily life and industry. The universality of the Schrödinger equation also demonstrated the power of fundamental principles. Unlike Bohr's model, which was limited to hydrogen-like atoms or early semi-classical approaches, the wave equation applied to an infinite range of systems. It could describe single electrons, multi-electron atoms, molecules, and even quasi-particles in solid-state physics. This universality was unprecedented, offering a consistent framework that united disparate observations under a single mathematical roof. The birth of the equation was not just the creation of a tool, it was the birth of a new paradigm in understanding the natural world, one in which continuity, probability, and mathematics coalesced into a coherent vision. Schrödinger's focus on purpose also reflected his desire for clarity and insight. He was not content with formalism for its own sake. He wanted the equation to provide understanding. It had to reveal why atoms are stable, why electrons occupy specific energy levels, and why matter behaves as it does at the smallest scales. The Schrödinger equation succeeded because it achieved this goal. It did not merely fit experimental data, it explained it. The discrete spectra of atoms, the formation of chemical bonds, the interference patterns of electrons and photons, all these phenomena could be derived from the principles embedded in the wave function. The purpose of the equation, therefore, was dual: to calculate and to illuminate, to predict and to explain. The historical context of its development also highlights its revolutionary nature. Schrödinger worked during a time of intense debate and rapid discovery in quantum physics. Competing theories, experimental anomalies, and philosophical disagreements created a field in flux. By introducing wave mechanics and the Schrödinger equation, he provided a stabilizing framework. It offered continuity in a field marked by discontinuity, coherence where there had been fragmentation, and a visualizable representation where abstraction dominated. The equation's birth marked the point at which quantum mechanics became a mature discipline, capable of both prediction and explanation, rather than a collection of empirical rules and paradoxes. Furthermore, the Schrödinger equation influenced how future generations approached science. It demonstrated the power of combining mathematical rigor with physical intuition, of seeking underlying principles rather than relying solely on observation or abstraction. Schrödinger showed that a single equation, derived from fundamental ideas, could illuminate an entire domain of nature. This approach set a precedent for theoretical physics, inspiring generations of scientists to search for unifying principles that explain diverse phenomena. The equation's birth was, in this sense, not merely a technical achievement but a philosophical and methodological milestone in science. In addition, the equation's development bridged gaps between disciplines. Chemistry, physics, and later biology all benefited from wave mechanics. Schrödinger himself recognized the interdisciplinary potential of his work, noting that understanding the fundamental behavior of electrons could shed light on chemical bonding, molecular structure, and even the principles underlying life itself. His later reflections on what is life drew upon the ideas embedded in wave mechanics, suggesting that the Schrödinger equation provided a foundation not only for physics, but for understanding complex systems and biological processes. The equation's purpose, therefore, extends beyond isolated particles to the broader architecture of the natural world. Ultimately, the birth of the Schrödinger equation represents a fusion of imagination, mathematics, and physical insight. Schrödinger envisioned a universe governed by waves of probability, formulated that vision into a rigorous mathematical structure, and demonstrated its predictive and explanatory power. The purpose of the equation was to unify, clarify, and illuminate, to turn the enigmatic world of quantum phenomena into something coherent, understandable, and actionable. Its creation stands as a testament to the power of human intellect to penetrate the invisible, to transform paradox into principle, and to reveal the deep structure of reality. Through this equation, Schrödinger gave science a tool that would forever change how we understand the universe, the atom, and the very nature of existence itself. The Schrödinger equation did more than provide a mathematical description. It redefined the very way scientists perceive matter and energy. Before its inception, electrons and other subatomic particles were thought to behave like tiny billiard balls, obeying deterministic rules akin to classical mechanics. Experiments, however, consistently contradicted this assumption. Electrons produced interference patterns in double-slit experiments. Spectral lines emerged in discrete steps rather than continuous distributions, and phenomena like tunneling suggested that particles could appear in places classical physics would forbid. Schrödinger recognized that these anomalies were not failures of observation or limitations of experimental apparatus. They were signals of a deeper, wave-like reality. The equation he developed captured this reality, showing that the behavior of particles could be described as continuous, evolving waves whose squared magnitudes indicated probabilities of locating particles in space and time. By encoding uncertainty within a rigorous mathematical framework, Schrödinger demonstrated that probability, far from being a flaw, was a fundamental feature of nature. One of the most significant impacts of the equation was its universality. While early quantum models applied only to the hydrogen atom or other simple systems, Schrödinger's formulation applied equally to multi-electron atoms, molecules, and more complex structures. By incorporating potential energy, kinetic energy, and temporal evolution within a single framework, the equation allowed physicists to calculate states, energies, and transitions in an almost limitless variety of systems. This universality meant that wave mechanics could bridge the gap between atomic physics, chemistry, and even emerging fields in condensed matter physics. It provided a common language that united previously fragmented areas of study, enabling researchers to communicate complex ideas and solve problems that had once seemed intractable. The predictive power of the Schrödinger equation was revolutionary. Spectroscopic data that had puzzled scientists for decades became understandable in terms of wave functions and probability amplitudes. Electrons were no longer imagined as tiny planets orbiting a nucleus. They were described as waves occupying regions of space defined by their energy and boundary conditions. Each allowed state corresponded to a specific wave pattern, explaining why atoms emitted or absorbed photons at discrete frequencies. Chemical bonding, previously guided by empirical rules, now followed naturally from wave interactions. Overlapping wave functions created stable molecules, while interference effects explained reactivity and bond strength. In effect, Schrödinger transformed chemistry into a science grounded in first principles, uniting the microscopic behavior of electrons with macroscopic chemical phenomena. The philosophical implications of the equation were profound. In classical mechanics, the universe was deterministic. Given complete knowledge of a system at one time, its future could, in principle, be predicted exactly. Schrödinger's wave mechanics challenged this notion. While the evolution of the wave function itself is fully deterministic, The outcomes of measurements derived from it are inherently probabilistic. This distinction reshaped the very concept of causality. The universe, at its core, was not entirely predictable. Probability became a central principle, and certainty became a concept limited to large-scale averages rather than individual events. Schrödinger's equation thus provided a framework in which uncertainty was not a defect of human knowledge, but a fundamental feature of the physical world. Another critical contribution of the Schrödinger equation was its role in visualizing quantum systems. Classical mechanics offered an intuitive picture of reality, but early quantum mechanics, especially matrix mechanics, was abstract and difficult to interpret. Schrödinger's wave function allowed for a more intuitive representation. Electron clouds, probability densities, and orbital shapes could be visualized, providing insight into the structure and behavior of atoms and molecules. These visualizations were not merely pedagogical tools, they guided experimental design, influenced chemical synthesis, and informed technological development. For the first time, scientists could see the quantum world in a meaningful way, bridging the gap between abstract theory and observable reality. The equation also underpinned an entirely new approach to understanding energy and motion. Classical physics assumed continuous energy distributions, but quantum phenomena exhibited discrete energy levels. Schrödinger explained this by treating electrons as standing waves in a potential well. Only certain wavelengths, and therefore certain energies, could exist stably, analogous to the harmonics of a vibrating string. This insight explained atomic spectra, electron configurations, and the stability of matter in a mathematically rigorous way. The quantization of energy emerged naturally from wave mechanics, no longer requiring arbitrary postulates or assumptions. Schrödinger's equation, therefore, did more than model reality, it illuminated the fundamental principles governing it. The equation's influence extended far beyond atoms and molecules. Condensed matter physics, the study of solids, liquids, and complex materials, relies heavily on the principles of wave mechanics. Electrons in solids form energy bands, their behavior described by solutions to the Schrödinger equation within periodic potentials. Understanding these bands is crucial for semiconductors, superconductors, and nanomaterials. Devices such as transistors, solar cells, and lasers are all designed using principles derived from the equation. Even quantum computing, which manipulates quantum states to perform calculations, depends directly on the deterministic evolution and probabilistic interpretation of wave functions. The Schrödinger equation, born from theoretical curiosity, thus became the foundation for technologies that define modern life. The conceptual leap required to accept the Schrödinger equation was enormous. Classical intuition fails when applied to microscopic systems. Electrons do not follow definite paths, they exist as superpositions, occupying multiple possibilities simultaneously. Measurement collapses this superposition into a single outcome. Schrödinger's work forced scientists to abandon the comforting notion of objective determinism at small scales and to embrace a universe governed by probabilities and wave dynamics. His equation provided the structure necessary to navigate this counterintuitive world, offering both predictive power and conceptual clarity. Without it, quantum mechanics would have remained a set of fragmented observations rather than a coherent, unified theory. In addition, the Schrödinger equation played a critical role in the development of computational methods. Solving the equation analytically is feasible only for the simplest systems, but approximate and numerical solutions allow physicists to tackle extremely complex problems. Computational chemistry, molecular modeling, and quantum simulations all depend on applying the principles of wave mechanics to systems of increasing complexity. By providing a clear mathematical foundation, Schrödinger enabled generations of scientists to explore domains previously inaccessible to human thought. His equation thus serves as a bridge between abstract theory and practical application, between the invisible quantum world and the tangible technological advancements that arise from it. The philosophical challenges raised by the equation also inspired thought experiments and debates that continue to this day. Schrödinger himself was aware of the tension between deterministic evolution of the wave function and probabilistic measurement outcomes. His famous cat paradox illustrates the difficulty of interpreting a system that exists in a superposition of states until observed. These debates forced the scientific community to confront questions about reality, observation, and the role of consciousness in quantum mechanics. The Schrödinger equation, while precise and deterministic mathematically, introduced uncertainty conceptually, demanding new ways of thinking about knowledge, reality, and the limits of scientific explanation. The impact of the equation on education and scientific methodology cannot be overstated. It became the central tool for teaching quantum mechanics, providing students with a unified framework to understand wave functions, probability distributions, and energy quantization. By framing microscopic phenomena in terms of waves and probabilities, it enabled learners to transition from classical thinking to quantum reasoning. The equation also influenced the methodology of research, guiding experimentalists in designing measurements, predicting outcomes, and interpreting data. It became a touchstone of scientific practice, a framework within which both theory and experiment could interact coherently. Moreover, the Schrödinger equation inspired further theoretical development. It laid the groundwork for quantum field theory, the study of many particle systems, and advanced models of atomic and molecular interactions. The principles embedded in the equation continue to guide research in particle physics, condensed matter, quantum optics, and emerging fields such as quantum information science. Every advance in understanding quantum phenomena, from electron tunneling to entanglement, relies fundamentally on Schrödinger's formulation. His work provided a foundation that allows physicists to explore deeper layers of reality with confidence in the mathematical and conceptual framework. Finally, the purpose of the Schrödinger equation extends beyond immediate scientific application. It represents a shift in worldview, a recognition that the microscopic universe is governed by waves, probabilities, and interactions that defy classical expectation. It embodies the unity of mathematics and physical reality, offering both predictive power and explanatory depth. The equation allowed humanity to move beyond simple observation into a realm where the fundamental principles of existence could be articulated, tested, and applied. It transformed quantum mechanics from a collection of rules into a coherent theory capable of describing, predicting, and even shaping the microscopic world. Through the Schrödinger equation, the invisible becomes calculable, the uncertain becomes structured, and the wave, like essence of nature, is revealed in all its elegance and complexity. One of the most famous thought experiments in the history of science, Schrödinger's cat, emerged from Erwin Schrödinger's desire to illustrate the strange consequences of quantum mechanics and the paradoxes that arise when microscopic principles are applied to macroscopic objects. At its core, the thought experiment was designed to challenge the prevailing Copenhagen interpretation, which suggested that a quantum system remains in a superposition of states until it is observed. Schrödinger found this notion deeply unsettling, as it implied that an unobserved particle could simultaneously occupy multiple contradictory states, and he sought a vivid way to convey the absurdity of taking this principle literally at larger scales. In his scenario, a cat is placed in a sealed box along with a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the Geiger counter triggers the release of poison, killing the cat. If it does not decay, the cat remains alive. According to the Copenhagen interpretation, until the box is opened, the atom is in a superposition of decayed and undecayed states, and therefore, the cat itself is simultaneously alive and dead, a proposition that seems nonsensical when applied to a tangible, everyday object. The brilliance of Schrödinger's cat lies not in the mechanics of the setup, but in the way it exposes the conceptual tension between quantum mechanics and classical intuition. At the atomic level, superposition and uncertainty are well established and experimentally verified. Electrons, photons, and other particles behave in ways that defy classical determinism. Yet when these principles are extrapolated to objects we can see and touch, the idea of a cat being both alive and dead challenges our understanding of reality. Schrödinger intended this paradox to provoke reflection on the interpretation of quantum mechanics, to force scientists to confront the question of whether the wave function describes reality itself or merely our knowledge of a system. The thought experiment effectively illustrates the counterintuitive nature of quantum superposition. While mathematically sound, its philosophical implications can appear absurd when applied outside the microscopic realm. Beyond its philosophical impact, the cat paradox also highlights the role of measurement and observation in quantum theory. In Schrödinger's framework, a quantum system evolves according to deterministic wave equations, but the act of observation collapses the wave function, forcing the system into a single definite state. The paradox demonstrates the profound consequences of this principle. If observation determines reality, then the line between what exists independently and what exists because it is measured becomes blurred. Schrödinger's cat raises the uncomfortable question of whether reality is objective or whether it is in some sense created through observation. This challenge has sparked decades of debate among physicists, philosophers, and theorists seeking to reconcile the deterministic evolution of wave functions with the probabilistic outcomes of measurements. The thought experiment also inspired new interpretations and approaches to quantum mechanics. It prompted discussions of decoherence, the process by which quantum superpositions interact with their environment, effectively preventing macroscopic objects from appearing in paradoxical states. It has influenced alternative interpretations, such as the many worlds hypothesis, which posits that all possible outcomes of a quantum event exist simultaneously in branching parallel universes. In these frameworks, the cat is alive in one universe and dead in another, avoiding the seeming contradiction in our observable reality. Schrödinger's insight, therefore, continues to shape modern physics, illustrating the necessity of understanding how microscopic rules translate to the macroscopic world. Ultimately, Schrödinger's cat is more than a quirky illustration. It is a profound commentary on the conceptual foundations of quantum mechanics. By taking the counterintuitive principle of superposition and applying it to a familiar, tangible object, Schrödinger forced the scientific community to examine the limitations, assumptions, and interpretations of quantum theory. It remains one of the most enduring symbols of the tension between quantum probability and classical reality, a vivid reminder that the microscopic world operates according to rules that challenge human intuition, and that understanding the universe requires both rigorous mathematics and philosophical reflection. Erwin Schrödinger, renowned for his groundbreaking work in quantum mechanics, extended his curiosity and intellect beyond the realm of physics into the mysterious world of biology. In 1944, he published his influential book, What is Life?, which sought to explore the physical principles underlying living organisms. Schrödinger's aim was to bridge the gap between physics and biology, to understand how the seemingly chaotic, ever-changing processes of life could arise from orderly, law-governed physical systems. At a time when molecular biology was still in its infancy, and the structure of DNA was unknown, Schrödinger's insights were both visionary and profoundly influential. He proposed that life operates through a form of molecular order that he called a periodic crystal, a structure capable of storing hereditary information and guiding biological processes with remarkable precision. This idea provided a conceptual framework that would inspire future generations of biologists, chemists, and physicists, ultimately contributing to the discovery of the double helix and the field of molecular genetics. Schrödinger's perspective was deeply rooted in his understanding of physics. He reasoned that the processes of life, although appearing complex and unpredictable, must ultimately obey the laws of quantum mechanics and thermodynamics. He was particularly fascinated by the question of how living organisms maintain order and stability in the face of entropy, the natural tendency toward disorder described by the second law of thermodynamics. He introduced the notion that organisms feed on negative entropy to sustain their highly organized states, extracting energy from their environment to counteract disorder. This conceptual leap allowed Schrödinger to frame life as a physical phenomenon, one that could be analyzed, predicted, and understood through the principles of modern physics. By highlighting the role of order and information in living systems, he set the stage for a new scientific approach that connected molecular structure to biological function. One of Schrödinger's key contributions was his emphasis on the genetic basis of life as a form of coded information. He suggested that hereditary material must be capable of storing information with great fidelity while being sufficiently flexible to allow for mutation and evolution. This concept of a molecular code anticipated the later discovery of DNA as the carrier of genetic information. Schrödinger's idea of an periodic crystal provided a model for a molecule that could maintain stability while encoding complex instructions for development and reproduction. Although the molecular details were unknown at the time, his theoretical framework guided experimentalists toward the search for such structures, influencing researchers like James Watson, Francis Crick, and Rosalind Franklin in their groundbreaking work on the double helix. Beyond genetics, Schrödinger's reflections extended to broader questions about the principles of life itself. He explored how physical laws could give rise to self-replicating, adaptive systems capable of evolution and complex behavior. His insights emphasized that living systems are not exceptions to physical laws, but manifestations of them, operating at the intersection of order and fluctuation. By applying concepts such as stability, energy flow, and molecular structure to biological phenomena, Schrödinger demonstrated that the mysteries of life could be approached scientifically without resorting to metaphysics or vitalism. His work thus helped legitimize the study of life through the lens of physics and chemistry, inspiring interdisciplinary research that continues to this day. The impact of Schrödinger's ideas extended far beyond theoretical biology. His vision motivated the development of molecular biology, genetics, and biophysics as integrated scientific disciplines. Researchers began to investigate the molecular mechanisms of heredity, enzyme function, and cellular structure, guided by the understanding that living systems are organized, information-driven, and fundamentally physical. Schrödinger's insights also influenced the conceptual framework of bioinformatics and systems biology, where the principles of information storage, processing, and transmission are central. His recognition of the informational and physical dimensions of life created a foundation for modern biology, shaping both experimental approaches and theoretical thinking. Schrödinger's contribution to biology illustrates the remarkable breadth of his intellect. While he is most widely known for his work in quantum mechanics, his application of physical principles to the study of life demonstrates a rare ability to cross disciplinary boundaries and illuminate entirely new fields of inquiry. He showed that the laws governing atoms and molecules could provide profound insights into living systems, and that the mysteries of heredity, stability, and organization could be explored scientifically. By connecting physics and biology, Schrödinger not only advanced our understanding of life, but also inspired generations of scientists to seek unifying principles across disciplines. His work in What is Life remains a testament to the power of interdisciplinary thinking, showing that the mind capable of revealing the quantum world could also glimpse the fundamental essence of life itself. Erwin Schrödinger was not only a physicist of extraordinary mathematical talent, but also a thinker deeply engaged with the philosophical questions raised by quantum mechanics. Throughout his life, he pondered the nature of reality, the role of consciousness, and the limits of human understanding, seeking to reconcile scientific knowledge with the profound mysteries of existence. The strange behavior of quantum systems, the probabilistic nature of particles, and the paradoxes illustrated by his own cat thought experiment led him to question whether the classical conception of an objective, observer, independent reality was adequate. Schrödinger's reflections suggest that the act of observation is not merely passive. It may be intimately connected to the very fabric of the phenomena being observed. He explored the notion that consciousness could play a fundamental role in shaping reality, not in a mystical sense, but as a necessary component in the description of quantum systems. Central to Schrödinger's philosophical inquiry was his engagement with the concept of superposition. He recognized that the wave function, which governs the behavior of quantum systems, allows entities to exist in multiple states simultaneously. While this is mathematically coherent, it challenges intuitive notions of reality. Schrödinger questioned whether physical objects possess definite properties independent of observation, or whether the act of measurement itself plays a role in determining outcomes. His famous thought experiment, illustrating a cat that is both alive and dead until observed, was designed to provoke reflection on the limits of classical logic when applied to the quantum world. It exemplified his concern that the microscopic rules of physics have profound implications for how we understand reality itself. Schrödinger also engaged with the idea that consciousness and the mind are inseparable from the phenomena they perceive. He was influenced by Eastern philosophies and the notion of a unified awareness underlying all experiences. In his writings, he suggested that consciousness might not be a mere byproduct of neural processes, but a fundamental feature of existence, interwoven with the universe in ways that physics alone could not fully describe. While he remained committed to scientific rigor, he acknowledged that human perception and the structure of observation could limit the extent to which we apprehend reality. This reflection positioned him uniquely among physicists as he straddled the line between empirical investigation and metaphysical inquiry, emphasizing that the mysteries of the universe extend beyond equations and experiments. In exploring the relationship between observation and reality, Schrödinger challenged the purely objective view of nature that dominated classical science. Classical physics assumed that particles, forces, and fields exist independently of observers, and that the universe unfolds deterministically according to fixed laws. Quantum mechanics, particularly as revealed through the Schrödinger equation and the principle of superposition, complicates this picture. Schrödinger realized that observation is not simply the act of recording pre-existing facts, it interacts with systems in ways that shape outcomes. This insight raises deep questions about the limits of knowledge, the role of the observer, and the boundary between subjective experience and objective reality. His philosophical reflections suggest that the universe cannot be fully understood without acknowledging the interplay between consciousness and measurement. Schrödinger's engagement with philosophy also extended to questions of unity and interconnectedness in nature. He proposed that all entities are part of a singular, unified reality, and that distinctions between separate objects are, in a sense, conceptual rather than absolute. This perspective offered a framework for understanding quantum entanglement, non-locality, and other phenomena that defy classical separation. By integrating these ideas into his reflection on consciousness, Schrödinger provided a vision of the universe as a holistic, interconnected system, where the observer is not detached but intrinsically linked to the observed. His reflections inspired later explorations of the philosophical and foundational implications of quantum theory, influencing thinkers in both physics and philosophy. Ultimately, Schrödinger's philosophical contributions reveal a mind deeply concerned not only with the mechanics of the universe, but with its meaning. He sought to understand how the fundamental principles of quantum physics relate to human experience, perception, and consciousness. His reflections continue to provoke debate and inspire inquiry, reminding us that the study of the physical world is inseparable from the questions of how we know, perceive, and interpret it. Schrödinger demonstrated that science and philosophy are not opposed but complementary, and that the quest to comprehend the quantum universe inevitably leads to profound contemplation of reality, awareness, and the nature of existence itself. Erwin Schrödinger's influence on science extends far beyond his lifetime, leaving a legacy that encompasses physics, philosophy, biology, and the broader understanding of reality itself. As one of the founding figures of quantum mechanics, he transformed the way humanity perceives the microscopic world. His development of wave mechanics and the Schrödinger equation provided a precise and elegant mathematical framework for understanding particles as waves, revolutionizing the study of atoms, molecules, and subatomic phenomena. These contributions laid the foundation for countless discoveries, enabling scientists to predict energy levels, electron distributions, and chemical interactions with remarkable accuracy. Schrödinger's work provided a universal tool, applicable across disciplines, and became a cornerstone of modern physics and chemistry, shaping the trajectory of scientific thought in the 20th century and beyond. Beyond the technical and scientific achievements, Schrödinger's legacy is deeply philosophical. His thought experiments, reflections on superposition, and explorations of consciousness challenged scientists and thinkers to question the assumptions underlying classical physics. By presenting paradoxes such as the cat thought experiment, he forced the scientific community to confront the limits of intuition and the role of observation in defining reality. Schrödinger's engagement with questions of consciousness, the unity of nature, and the interconnection between observer and observed encouraged a more nuanced understanding of the relationship between knowledge and reality. His work bridged the gap between empirical science and philosophical inquiry, illustrating that the study of nature inevitably raises questions about perception, existence, and the nature of understanding itself. Schrödinger's impact on biology represents another dimension of his enduring legacy. In What is Life? He applied principles from physics to living systems, exploring how molecular structures could store and transmit hereditary information. His idea of the aperiodic crystal anticipated the discovery of DNA's double helix and influenced the emergence of molecular biology. By emphasizing the importance of information, order, and energy in biological systems, Schrödinger provided a framework that guided research in genetics, biophysics, and systems biology. His vision inspired scientists to see life as a physical phenomenon governed by fundamental laws, encouraging interdisciplinary approaches that integrated physics, chemistry, and biology in the pursuit of understanding. Technologically, Schrödinger's contributions have had far-reaching implications. Wave mechanics underlies modern electronics, semiconductors, lasers, superconductors, and quantum computing. Devices that define contemporary life, from smartphones to medical imaging technologies, rely on principles derived from his work. By providing a framework to predict and manipulate quantum behavior, Schrödinger enabled innovations that transformed science, industry, and society. His legacy, therefore, is not confined to abstract theory. It manifests in practical applications that continue to shape human experience, highlighting the enduring relevance of his insights in both research and technology. Furthermore, Schrödinger's influence persists in education and scientific methodology. His approach demonstrated the power of combining mathematical rigor with physical intuition, inspiring generations of physicists and researchers to seek unifying principles across disciplines. By showing that complex phenomena can be described through coherent, elegant frameworks, he set a standard for theoretical exploration and experimental design. Students of quantum mechanics, molecular biology, and interdisciplinary science continue to encounter his ideas as foundational, ensuring that his impact on intellectual thought extends well beyond his era. Perhaps most importantly, Schrödinger's legacy embodies the courage to question, explore, and imagine beyond conventional boundaries. He refused to accept incomplete or purely heuristic explanations, striving instead for conceptual clarity and mathematical precision. His work illustrates the power of curiosity, the importance of bridging disciplines, and the enduring value of addressing not only technical problems, but also the deeper philosophical questions that arise from them. Schrödinger demonstrated that a single mind, guided by insight, creativity, and rigorous reasoning, can illuminate entire fields of human knowledge. In sum, Erwin Schrödinger's lasting legacy is multifaceted. He reshaped quantum physics, influenced the philosophical understanding of reality, guided the emergence of molecular biology, and laid the groundwork for technologies that define the modern world. His contributions continue to inspire scientific discovery, philosophical reflection, and intellectual curiosity, ensuring that his name remains synonymous with profound insight, interdisciplinary vision, and the relentless pursuit of understanding the universe. Schrödinger's work reminds us that science is not merely a collection of facts, but a dynamic exploration of reality, knowledge, and the possibilities of human thought.